trying to do the Frobenius method, and what is it about? So last time we were talking about series solution, right? We were talking about the case where you have your function written as a0 plus a1x plus a2x squared plus a3x cubed, and so on and so on. Okay, that was a series solution, and the reason for doing this was because a lot of the differential equations, when it gets complicated enough, the solutions are not the Bessel. The solutions are not the exponential functions, trigonometric functions, or any kind of functions that you know of. Okay, rather you have very exotic functions called like Bessel functions, area functions, hypergeometric functions. All these functions you've never learned about. Okay, and because of that, rather than trying to write down their function itself, you want to just think about them as power series and just plug them in as a power series, and you want to find the solutions like that. However, although this can represent many different types of functions, it's just like it's called expressiveness. I mean, if you, a painter who can draw well can express all kinds of stuff, right? So the better tools you have, you can express more stuff, and therefore the more expressive you are, you can represent a whole lot of possible solutions that such and such differential equation could have. However, the problem is that this is not as expressive as you think, because, for example, a simple equation like square root of x does not possess any power series. The reason that this doesn't have a power series in this form is because it's not differentiable at 0. If you differentiate, you get this, and if you plug in 0, you get infinity, right? So even simple functions like this do not have a power series, and therefore you want to modify this a little bit so that you can even include cases like this. And therefore, Frobenius thought about the following case. What if you included not only these power series, but power series multiplied by some x to the r? So it's the same thing as before, but you have this extra x to the r, where r could be any number, any real number. So r could be, say, a rational function, rational number like 1/2, or it could be a negative, right? In case where you have a function that starts with 1 over x. For example, let's see. Here's an example. 1 over x times 1 minus x is same as 1 over x plus 1 plus 1 over x plus x squared plus like this. Okay. So there are functions which not only starts at the constant term. Some functions start at 1 over x. So this will be the case where you have x to the negative 1 times 1 plus x squared, and so on and so on. Okay. Now, it might not occur to you why this is same as this, but do you remember the geometric series? If you have a infinite geometric series with the first term a and common ratio r, what's the formula? A over 1 minus r, remember that? So this really is 1 over x times 1 over 1 minus x, and that's why it's the same as that one, okay? So, I mean, even simple functions like this cannot be expressed just by a power series. You need something more than a power series. And if you write an equation like this, then it's expressive enough that it contains functions like this, or square root of x, all kinds of much more functions. Of course, there are even more functions than this, but for those we will not even consider it. All right, so Frobenius method is a method that looks for solutions that can be expressed in this format, which if you write it using sigma notation, it's x to the r times sigma, n from 0 to infinity of a n x to the n. Now when r is 0, what does this become? If r is 0, what does this become? What's x to the 0th power? 1. So it becomes a regular power series, right? So this can express any power series plus the other functions that cannot be expressed using power series. That's why this is better than the previous one. Of course, trying to figure out this type of solution will need more work than the regular ones. That's why you really want to use this only when it's necessary. And we will actually talk about something called singularities, which can let you know ahead whether you need really this form of solution or you can just live with just this by itself. It all has to do with the fact that for this equation, x equal to 0 makes this y double prime go away, right? If at x equal to 0, this goes away, right? In such a case, you say this differential equation has a singularity. So I'm skipping that discussion. We will come back to that discussion about singularity, and later you will be able to know when we should be looking for this type of solution and when we don't have to. Okay? So that discussion will be for later. Today we'll just go on and try to look for this type of solution for that one and see how far we can go with it. Okay? All right, so let's begin. Here's the real solution. That was just an introduction why we are looking for such a thing. All right, so suppose for some reason you know that this equation will have a solution like that. How can we find out the actual equation? Here's how it works out. First, you say y is x to the r sigma a n x to the n from 0 to infinity. And another condition that you can impose here is that you can say that a0 is not equal to 0. That's a condition that you can impose on here. So our requirement is that the function that's a solution to this looks like the following, with additional condition that a0 is not equal to 0. Now, that's because if this happens to be 0, and this happens to be 0, and let's say for x squared, let's say you get the first term which is not 0. In such a case, so think about an example like this. Suppose you found a solution that looks like that's a solution to that one. It's not, but suppose that this is a solution. If the first few terms are 0, and it starts to be non-zero from here, and after that all the numbers are non-zero, or some could be 0 still, but if you get the first non-zero term here, you can rewrite this as x to the 2 plus 1/2 times 3 times x to the 0th power plus, let's just write something here, 5x cubed, and this will be just 5x first. So you can redefine this to be a0, this to be a1, and by doing that you can make the first term to be non-zero. You can force the first term to be non-zero by redefining your value of r. Okay? Yeah, this one may not be so clear if you don't see the solution. Okay? All right. if you understood it, that's great. If you didn't, just accept it as one of the conditions. Okay?
You just did 2 because there was 2 zeros for the first.
Yeah. So you can basically what I'm trying to say is that if A0 happens to be 0, you can redefine the value of R to be something else, so that this starts from the non-zero one. So that's the idea. Okay. That's a little technicality which actually will be important later at some point, but I don't know. If you understood it, that's great. If you didn't, let's just accept it and move on. Okay. All right. So if this is the solution you're looking for, what's y prime? Well, first you should rewrite this as sigma n from 0 to infinity of an x to the n plus r. Because I can multiply x to the r to x to the n, since they have the same base, the exponents add up. And then we differentiate, which brings down the n plus r and becomes n plus r minus 1. Now, you might remember that in the case of power series, when we differentiated, we started from 1. That was because when you plug in n equal to 0, this part vanished. Now that's not guaranteed because of this r here. Because if you plug in 0, 0 plus r is what you get, and r might not be 0. In this case, this is not 0. And for that reason, you don't start from 0. No, you don't start from 1, but you start from 0. Okay? So that's another thing that you have to watch out when you're trying to look for the Frobenius type. Another derivative will bring out another exponent. Again, you should start from 0, not from 2. That's an important distinction. So that's what you get when you start with the Frobenius form of the solution. Let's plug everything in here. But before you plug it in, you should break up any coefficient functions that has more than one term. So you should really break this up into 2. And then we will plug in everything. 2x squared sigma n from 0 to infinity n plus r minus 1 n plus r an x to the n plus r minus 2 plus 3x times sigma n from 0 to infinity of n plus r an x to the n plus r minus 1. And then minus x squared sigma an x to the n plus r n from 0 to infinity. And finally, you will have minus sigma n from 0 to infinity of an x to the n. And all that has to equal to 0. Now let's multiply things in there. So everything that was in front should be multiplied in to give you, let's see, sigma n from 0 to infinity of 2 times n plus r minus 1 n plus r an x to the n plus r. This thing going in will give you n from 0 to infinity 3x. Actually, x times x to the n plus r minus 1 will get rid of the minus 1 and give you just like this. And then plus sigma minus an x to the n plus r plus 2 from 0 to infinity minus sigma, actually plus negative an x to the n. Oh, I forgot to put a plus r here. Okay, I don't think I made any mistake so far. Okay. Now, which one requires a shifting? This one. This one's the only thing that requires shifting, right? The other ones, they all have n plus r, so the exponents are the same, except this one. So let's just shift this one and see what we get. What should we replace n by? N should be replaced by
n minus 2.
n minus 2, because n minus 2 plus r plus 2 will cancel the 2, and this will become n plus r. If you replace n by n minus 2, you'll get x to the n plus r. And this n has to be replaced by n minus 2. And then, because n minus 2 is equal to 0, if you solve that for n, what would you get? N equals 2. If you replace this n on the left by n minus 2 and solve the n minus 2 equal to 0 for n, you get what? N equals 2?
2.
2. So that's what you get after shifting. All right, now let's try to write everything down, including the shifting. Erase this. Write everything down. Okay. Sigma n from 0 to infinity of 2 times n plus r minus 1 n plus r an x to the n plus r plus sigma n equals to 0 to infinity n plus r an x to the n plus r. I forgot 3 here. And then plus sigma n from 2 to infinity of an minus 2 with the minus in front, x to the n plus r, plus sigma negative an x to the n plus r, n from 0 to infinity. And that has to equal to 0. That's the differential equation I get. Well, that's the equation I get once I plug in the Frobenius form. What was the Frobenius form again? It was y equals to sigma n from 0 to infinity of an x to the n plus r, where a0 is not equal to 0. That, if we plug this into this differential equation, and if we simplify everything, and after shifting, this is the equation I get. That's where we are at so far. Any questions so far? Okay. It's just long. Nothing is very complicated. It's just long. You just need patience, and you can get it. Okay. All right. Now let's try to write down what we get for individual n's. So first, n equals to 0. What happens at n equals to 0? When n is equal to 0, what happens?
First, the second, the third, the fourth.
First, second, and
The fourth.
fourth will produce something, right? What would it produce? It produces 2 times r minus 1 times r times a0 plus 3 times r times a0 minus, this is nothing, so this one doesn't produce anything, but then this last one minus a0 times x to the r is equal to, is what you get when n is equal to 0, right? And then plus, what happens for n equals to 1? So maybe I should write these in red, because that's not part of the, this is like an annotation, not really the part where you're calculating.
The same deal for second and fourth.
Yeah, first, second, and fourth the third one still doesn't produce anything, right? So for n equals to 1, you get 2r, r plus 1, a1, plus 3r plus 1, a1, minus, that doesn't produce anything, and then the last one, a1, x to the 1 plus r. So that's what you get.
Must be r plus 1 or r
Yeah, n is 1, right? So 1 plus r, 1 plus r minus 1, so that's r and r plus 1. Any other questions?
Why do you skip that space?
Oh, because this thing starts from n equals to 2. At
So-
level n equals to 0, this doesn't produce anything.
Could we just put plus 0 there?
If you want, but that's not necessary. Doesn't do anything. Okay, and then what happens after 2? Then everything produces terms, right? So we can write the remaining as a sigma, starting from n equals to 2 to infinity, you get 2 n plus r minus 1, n plus r, plus 3 times n plus r, and then let's put this one too, minus 1 times an. These are the ones, so first, second, and the last ones are terms that contain an. And this one is minus an minus 2, and all of them have x to the n plus r multiplied. Okay, so what we did was I just rewrote this summation, this plus this plus this plus this, into this plus that. Okay? So if you have trouble understanding what's going on, what you can do is you can write all the terms by starting from this one. So n equals to 0, n equals to 1, n equals to 2. Just write all the sums, okay? All the terms, starting from here. And then you do, starting from 0, 0, 1, 2, 3, 4, you write all the terms down. This one starts from 2, so 2, 3, 4, 5, 6, 7, write all the terms. 0, 1, 2, 3, 4, 5, you write everything, okay? And just for safety, just do it for until n equals to 10 or something, just if you have the time. And you can do the same thing from here. You can just multiply all these out, multiply this out, multiply these out, and from here 2, 3, 4, 5, 6, 7, 8, 9, 10. Just write all these terms out and compare the two. You will see that they're exactly the same. They're exactly the same. So I'm not lying or anything. It's very honest. This left side is exactly the same as the right side. Now, we're still saying that this is equal to 0, right? Now, one of the things in things you can prove by mathematics is that for this to be 0 for all values of x, or some for x belonging to an interval, all of these individual coefficients must be 0. So we get the following identities. We know that this has to equal to 0. So all these will turn into equations. Okay? So I should be, yes?
The last thing you wrote, that's just for n is greater than or
2
equal
or
to.
greater, right. It's starting from 2 to infinity, yes.
We only have 5 minutes left.
Okay, yeah. All right. It's starting from 2 to infinity, okay? All right, so now, I should be writing all this down again, but since we don't have enough space, let me just alter this and say this should be 0, this should be 0, this should be 0. You get each individual thing. Now let's try to see what this one brings us. Now if I factor the a0 out, and then if I multiply these out, it's 2r squared minus 2r plus 3r minus 1 is equal to 0. So if we have a0 times 2r squared plus r minus 1 equal to 0, which actually has two solutions. This factors into 2r minus 1, r plus 1 equal to 0. Actually, I should say here. Okay, so that factors into a0 times 2r minus 1 times r plus 1 equal to 0. And then for this to equal to 0, either r is 1/2 or r is -1. Well, there's the third case where a0 could be 0, but our assumption was that a0 cannot be 0. So either it has to be this or that. And for each individual ones, we should have a solution. Okay? However, Frobenius later found out that there are some technicalities if they differ by an integer. So we're going to go there. Okay. In most cases, I'll just ask you to find one solution. I mean, you know, there should be two linearly independent solutions because it's the second order, right? And each individual ones will give you one solution each, so that you get two linearly independent ones. But if I say just find one solution using the Frobenius method, then you can just choose one of them, the higher one. Usually, if you take the higher one, it always exists. If you take the lower one, there's some very special cases where you don't get a solution. So this we're going to take, and then using that, we're going to plug it into the other ones to get to. Maybe we should.
So stop and start it again.